Okay, now we're going to look at a special application of equilibrium and equilibrium expressions. We're going to kind of just get our feet wet with this. We'll come back to solubility equilibria a little bit later on and go a little more in depth with it. But what I want to do now is kind of just show you how we can apply the concepts of equilibrium to a particular type of situation. We will go further in the next chapter and apply it to another specific type of situation, mainly acids and bases. But for this one, we're going to start out with what I think is a more simpler application, and that is looking at the dissolving process. So we're going to look at the equilibrium situation that exists when you are dissolving a solid. And the ones we're going to be dealing with in this unit are aqueous situations. Okay, solubility product. This applies to solids dissolving to form aqueous solutions. And we're going to define the equilibrium constant for this situation as the KSP, or the solubility product constant. Now, in looking at these, so here is a typical equation for the dissolving process. In this case, it is solid silver chloride. We dissolve it and we get aqueous silver ions, aqueous chloride ions, and we get them in a 1-to-1 ratio. Okay, so we would write this the same way as we would write any equilibrium expression, products over reactants. But in this case, and in the case of all of these solubility equilibrias, the reactant will always be a solid, and so it will not appear in our equilibrium expression. So here's some examples of some others. Okay, here we get 2 fluoride ions for every 1 magnesium, and so we take that into account. So we're still using law of mass action here. All right, here's another one, just so you can kind of get an idea of what we're doing here. Okay. Now, so let's tie this again back to things we've talked about. If we're talking about comparing a reaction quotient to our equilibrium constant, the KSP in this case, if Q is less than the KSP, we have an unsaturated solution. Okay. If Q is equal to KSP, we are at equilibrium, which means we are at a saturated solution. Remember, saturated means that we have the dissolving and the recrystallization processes are going on at the same rate. Okay. And then Q greater than the KSP is a supersaturated solution, and there we would get a precipitate or a recrystallization of the solute. Okay, so again, here we're looking at bismuth sulfide. All right, the solubility, new term here, that is the concentration of the bismuth sulfide that dissolves. And that's going to equal half of the bismuth ions and a third of the sulfide ions that would be present in the solution. Or you can also think of it as the moles per liter of bismuth in the solution is going to be 3 times the solubility of the bismuth sulfide. Okay, the solubility, it's going to be the moles per liter that dissolves. So for every 1 mole of bismuth sulfide that dissolves, I get 2 moles of bismuth ions and 3 moles of sulfide ions. Okay, the KSP, or our equilibrium constant, is a constant for a given temperature. However, the solubility can be variable. Again, this is similar to the fact that we can have many equilibrium positions that are defined by the single equilibrium constant. Alright, and this is just kind of a diagram of showing the types of calculations that we'll be doing and kind of the general process. In the top, if you have the solubility of a compound, then you can, if it's in grams per liter, you can convert that to the molar solubility of the compound. When you know molar solubility of the compound, you know the concentrations of the cations and anions in solution, and you can use this to find the KSP of the compound. Or conversely, if I know the KSP, I can use that to find the concentrations of cations and anions, and hence use that to find the molar solubility and the solubility of the compound. So those are the two types of equations or calculations that we'll be doing with these. Okay, so let's take a look at a couple of example problems here. Alright, wants to know what is the solubility of silver chloride in grams per liter, and I'm given the KSP. Well, for each of these, it's going to help if you write your expression, just so you kind of keep track of what's going on. Okay, and that means my KSP would be equal to silver and chloride. Okay, and so I'm given my KSP. Okay, so if the solubility of the silver chloride is X, okay, we get one silver ion, one chloride ion for each one formula unit of the silver chloride. So if the solubility of silver chloride is X, the silver ions would be X, the chloride ions would also be X. And taking the square root of both, I'm going to get 1.26 times 10 to the minus 5, and that's in moles per liter. Okay, and that would be my solubility of my silver chloride. Okay, what concentration of silver is required to precipitate only silver bromide in a solution that contains bromine and chloride ions at a concentration of 0.02 molar? This is similar when we get to where we're doing qualitative analysis. This is something called selective precipitation. In other words, if we had a mixture of bromide and chloride ions in a solution, one of the ways that we could separate them is to add enough silver to precipitate the bromine out and not the chloride. Now, why can we do that? Well, look at the two different KSPs. Okay, the higher the equilibrium constant, the more it favors products, or the more it's going to go in the direction of the products. Okay, so the silver chloride will stay dissolved in solution more so than the silver bromide with. Silver bromide has a lower equilibrium constant, so it's going to come out of solution first. So let's look at how we can deal with that quantitatively. Again, here's our equation that we're working with, and my equilibrium expression. Okay, so in this case, we have our KSP. We don't know what the silver molarity is, but we do know that we already have 0.02 molar of the bromine in solution. Okay, so we're going to put that in for our bromine concentration. And what that gives us is a silver concentration of 3.85 times 10 to the minus 11th moles per liter. Okay, so if we have one of our ions present, we're going to put that concentration into our expression. Okay. That, having one of our ions already present in solution, we call that a common ion effect. And this basically, the presence of a common ion is going to decrease the solubility of our salt. Okay, so let's look at why that would happen. If we have, just like what we had before, say this, so think about, from what we learned about Le Chatelier's principle, if I have, in this case, in B, alright, if I have a solution that has sodium bromide in it, and I'm trying to dissolve silver bromide, well, that means that I'm going to have more bromide in the solution. And what does Le Chatelier say is going to happen? It's going to shift it back towards the reactant. If I add bromine, it's going to shift it back towards the reactant. Okay, shifting it back towards the reactant means it's going to be less soluble. Okay, so let's quantitatively compare these two things. So if I was going to look at the solubility, let's see, our silver bromide, we had 7, okay, let's do this first. KSP is silver and bromine, and that's going to apply in both places, and that's going to equal, from before we said 7.7 times 10 to the minus 13. So let's look at, with water, how would we find that? Well, 7.7 times 10 to the minus 13, and if our solubility of the silver bromide is X, the solubility, or the concentration of the silver ions would be X, concentration of the bromine ions would be X. So we would get X squared, and that's going to give us a solubility of 8.77 times 10 to the minus 7. Now let's look at what happens if we have that common ion in there. So we set it up the same way, and so the silver is still going to be X, but now for the bromine, I have that concentration present, and when that's the case, I end up with 7.7 times 10 to the minus 10. So my solubility decreases just the way that Le Chatelier says that it would. Okay, let's look at a couple more problems. The ones we've had so far, the ratios of ions to the whole thing have been 1-to-1. But let's look at what happens if that's not the case. So here I have silver phosphate, and we're dissolving it. So it's going to have, you're going to get 3 silver ions and 1 phosphate for every formula unit here. So my KSP is going to be the silver concentration cubed phosphate times the phosphate. Okay, and it wants to know what mass of silver will be found in 29.9 liters of a saturated solution. So my KSP is 8.9 times 10 to the minus 17. Now, if the solubility of the whole thing, of the silver phosphate, we'll call it X. If it's X, then the silver ions would be 3X, and the phosphate ions would be X. So here we get, that's going to be 27X to the 4th. And that is going to give me an X of 4.26 times 10 to the minus 5th. Okay, that is our solubility of the silver phosphate. Okay, now I want to know specifically about the silver. Well, we already know 3 times that is going to give me the concentration of my silver ions. And that's going to give me 1.28 times 10 to the minus 4th moles per liter. Okay, and when I plug that in, to 29.9 liters, that gives me 0.00382 moles of the silver. And if you work that out with the molar mass of silver, you'll find that that is equal to 0.41 grams of silver. Okay, last problem. Here we have strontium arsenate. Solid. Dissolving. So we get 3 strontiums and 2 arsenates. Okay, so my KSP is going to equal the strontium cubed times the arsenate squared. Okay, now here I have the solubility of the strontium arsenate of the whole thing. It's 8.3 times 10 to the minus 5. Okay, I want the KSP. So if the whole thing is 8.3 times 10 to the minus 5, then the strontium concentration is going to be 3 times 8.33 times 10 to the minus 5 cubed. And then the arsenate would be 2 times 8.3 times 10 to the minus 5. Okay? And then we get 4.25 times 10 to the minus 19th. That would be moles per, no, sorry, that's the KSP, so that's going to be unitless. Okay, the biggest thing I think that people seem to have problems with these is just realizing the fact that you're going to treat, when you're finding concentration of the ions in terms of the solubility of the whole thing, that you're going to include that factor, like in this case that we get 3 strontiums for every one of the whole thing. You include that anytime you're figuring out the concentration of the ion here. This 3 that's here doesn't do away with the need to include that in here. Okay, and again, this is only when I'm defining the concentration of one of the ions in terms of the solubility of the whole thing. Okay, if I'm given the concentration of the ion, then I would put it in there and not be multiplying by 3. So that the reason I multiplied this by 3 is because the only concentration I had, or the solubility I had, referred to this whole thing. And so we know that when this dissolves, 1 mole of this is going to give us 3 moles of strontium, 2 moles of the arsenate. So if you're finding this concentration based on the solubility of the whole thing, then you have to multiply by the number of ions that you get for each of the ions.